rewind rather. So when we're dealing with these equations, what we're dealing with is p squared plus 2pq plus q squared equals 1. That's one of the equations. Do you understand that? So when we're talking about that, we're talking about what? What are we talking about when you see p squared, q squared, and 2pq? What are we talking about? You said it already. You started saying it already correctly. Go ahead. What else is it? What is it? That's right, the homozygous and heterozygous.
But it's
Which one is homozygous dominant? The p squared, right? Homozygous dominant. Which is the homozygous recessive?
Q squared.
The q squared. And the heterozygous is 2pq. That's what that equation means. You have to know that. What about this other equation? What does that mean?
The dominant
Allele frequency is correct. So yes. P is the dominant allele frequency. Sometimes you'll see allelic frequency, same word. Until my pencil refreshes, I'm gonna have to use my finger. So, and then the Q is a recessive, right? Allele frequency. What does that mean? Allele frequency. Frequency of the allele where?
in the population.
In the population. That's correct. Is everybody understanding this? Does anybody have an issue with what we're talking about? All right. So let's go ahead and take a look at that. Forget about that for a minute. So when we talk about the alleles in a population, what we're talking about is some kind of, and let me just go ahead and draw this as it's a pool, right? That's a pool. I'm gonna go ahead and try to draw a little better pool there. It's like a swimming pool, right? A pool. And in that pool, there are alleles. There's big A's, and there's little a's. And the number, how many alleles you have, what the frequency of the alleles are in this is your gene pool. This is all you have to draw from. If you want water, if you have a pool of water and you're in a village, the water comes from that pool. If you want to drink from that water, you have to take a bucket and go down to that pool and come and take it home to drink. Is that clear?
Yes.
So if you're going to make a new person, you only have these alleles to work with. So this is your gene pool. So what is a gene pool? It is a population. The genes in a population. That's what gene pool means. So when you see gene pool, you're talking about how many genes, how many alleles, and the percentage of those alleles are there in the population that you're looking at. Now you could be looking at an entire planet, or you could be looking at a village, or you could be looking at 5 people at a classroom. It doesn't matter. You have a gene pool, the size of the pool differs, but in that pool, that's your population. Is that clear to everybody? All right, so that's it. That's gene pool. Okay. You know what? I'm going to leave it there. I was going to delete it, but I'll leave it there. So you have a gene pool, and you have 90% A, get big A, 10% little a. So let's go ahead and do it. 90% big A. That's your what? What is that? What is big A?
P.
Is your dominant, right? If they put big A and little a, you know it's dominant recessive. And you have 10% little a. Are we good?
Yes.
All right. So they ask, what's the frequency of the individuals in a population that are this, big A, little a? All right, so they've told you the amount. What are these? What are these things? What do you see here? What would we call these? The percent of a big A and little a in a population. So what would you call that?
Gene frequency.
Gene pool or gene frequency, allele frequency, right? So that's right. So we would call it allele frequency
I know it was a little something.
in your what?
Gene pool.
Gene pool. Right? So when you talk about 90%, that means you're saying that 90% of your gene pool is big A, and 10% of your gene pool is little a. Are we okay with that? All right. Someone hand that to me, please. What is the frequency of individuals in a population then? Mr. Mendoza speaking, may I help you? I thank you very much, Ms. Hill. I appreciate it. Bye-bye. Oh, I want to send you so bad. Somebody who sat here last night, raise your hand if you were here last night, went over this. Send her. I got two of them. I want to send both of you go. There, I don't have to make a decision. Hurry up back, because I'm going to go into some detail. I don't want you to miss anything. So, and I want to quiz her. When we get back, I'm going to quiz her. She better get the right answer. What should we do to her? So we'll take her out. All right. All right, so what is the gene frequency of individuals in a population with a genotype of big A, little a? What is big A, little a?
Q squared, P squared.
Well, hold on. We're not there yet. Big A, little a is called what? What do we call this? Heterozygous. So our zygotes here would be big. They're hetero. They're different, right? All right. So what do we do? How are we going to figure that out? Somebody tell me. What are you going to use?
Figure out what heterozygous.
Go ahead. Somebody walk me through this. What do I do? Somebody, first step. Give me. Yeah. All right. I'm not going to use your names because I'd rather not embarrass anyone. So I'll just say, yeah, here, okay, or whatever. What did you say? So you're saying to take 0.9, where'd you get 0.9 times 0.1?
That's 0.9 is the P, 0.1 is the
So you're saying take 0.9 and multiply it times 0.1, and that's going to give you what? 0.09. That's what you want to do.
And then multiply by 2.
And then multiply that times 2, it gets you what? 0.18. Why did you do that?
Because yesterday it was 2PQ was for heterozygous.
Say that again?
Yesterday you said 2PQ was for heterozygous.
Well, let's go back and look at that. Let's figure that out. So I'd like to start from the beginning, all right? And let's see if he's right. He did some calculations. My problem with what he did, he didn't label any of the numbers, and so as he's doing it, can he check himself to make sure he did something right? He could easily make a mistake, right? And not even figure it out until he gets his grade back from the state saying that he didn't pass the test, right? So it hurts, right? That hurts. So let's walk through it and define, make the definitions, make sure we're doing everything right. So I got 90%. He said that he started with 0.9. I got 90% A. What am I going to do with that 90%? I'm going to do what?
Turn to a decimal.
Decimal. That's point. I'm going to move it from percentage to decimal. I move it twice to the left. That's right. So I got 0.90 for A, which is what? What is A? Dominant. All right. So that's a percent A. Is that P or Q?
You mean big A is dominant.
So is it P or Q?
P.
P. So there we have P. Now we have 10% little a, which is what? 0.1, which is recessive.
Which would be Q.
Q. So now we have P and Q. Do you agree? Is everybody okay with that so far? Okay, I'm good with it too. Oh, I hate when that happens. It groups it all together and then I have to. So there we go. So now we have a gene. Now what do we do? We got P and Q. How do we find out heterozygotes?
You got a times P, Q, then
What's the heterozygous? We defined it early on. 2PQ. 2 times P times Q. Right? Which equals 2 times what? 0.9 times 0.1. Unless you put a 0 in there, I guess. Significant digits. Do we agree that that's right?
Yes.
Everybody good? And that does equal what? 0.18. Right? So he was right. He would have got it right. My concern is that I don't want him doing that kind of sloppy math when you're, and I don't mean to insult you, but it's sloppy, right? Make sure you're defining your terms and you're walking yourself through it, because as smart as you are, as well as you understand it, a little mistake could cost you an easy answer on a test, right? Why get an easy answer wrong? And everybody makes a mistake, so don't think that you won't make a mistake. All right, so let's go and put these off to the side. Let's put all this off to the side here. All right, so let's go on to the next problem. If a population experiences no migration, is very large, has no mutations, has random mating, and there's no selection, no natural selection is what they mean, but also you can say no artificial selection either. By which of the following would you predict? What does all that mean?
That is not going to be no evolution
No evolution.
in the population.
There's no evolution in the population. That's what that means. There's no evolution in the population. Which means what? Let's think about what did we define evolution as? Not some crazy thing about monkeys turning to people. We're not saying about anything that yet. We're not there yet, right? What is evolution? What does evolution mean?
Change.
Change in gene frequency.
Change in gene frequency in a gene pool or in a population, right? So what does it mean if there's no evolution? There's no what?
Change.
There's no change in the gene frequency, and so that's what we would expect. Let's see if any of these match that. Let's just go, population will evolve, but much slower than normal. No, right? So we can just check that one off. No. The next one says, now why is that one wrong? Because we just said this is no evolution. When these are all true, there's no evolution. The makeup, that's Hardy-Weinberg, that's right. The makeup of the population's gene pool will remain virtually the same as long as these conditions hold.
Yes.
That's it. There's your answer. A lot of people did well on this quiz. The composition of the population's gene pool will change slowly in a predictable manner. No. Dominant alleles in a population's gene pool will slowly increase. No, right? Because if that happened, we'd call that evolution. And population probably is equal frequency of A's. This is not true. There's no way of telling that without measuring it, right? Are we all good with this so far? All right, so let's move on. So if you see that again, you're not going to tell me that you didn't understand or whatever. All right. The next one. Which of the following is not a condition that must be met by Hardy-Weinberg?
You need a number.
Right. You have to know what Hardy-Weinberg is. And you know what? What's funny is that the answer to 3 is right there. Number 2 is the answer is right there. So a large population size has to be true. So that's not the answer, because this is what tricks a lot of people. I can tell you there's 5 kids that have come to me and said, man, I got that wrong because I didn't see the word not. And you're lucky that they actually made it capital. Sometimes they don't even do that, all right? So 1 is correct, so that's not the answer. No mutations is correct, so that's not the answer. No immigration or emigration, so that's not the answer. Dominant alleles are more frequent than recessive alleles, and then no natural selection is the answer. So the right answer, because it's not, is this one. When you say there's more dominant than recessive or more recessive than dominant, by the way, I'm going to say it again, there is no guarantee that a dominant allele will be more frequent in the population. What determines that is evolution, natural selection. It's also some of the other things that we talked about, bottlenecking, right? What we call genetic drift, random deaths can change the gene frequency as well. But the gene, how many, whether dominant is more prevalent or recessive is more prevalent, all depends on the situation. I'll use the example again. If you have a dominant gene that kills you before you're born, how often do you think you're going to see it in the population? Literally none. Literally, you're always going to see the little a. You'll never see the big A because big A means, right, before you're even born. All right, so the population has immigration and emigration. This is an example. Which of the following?
Gene flow.
Gene flow. The answer is gene flow. Genetic drift is random, right? And it's random because of some event. The event could be a lot of different things. Sexual selection is wrong because that's because of somebody mating, right? Somebody choosing. The females are choosing the brighter bird or the bigger lion or whatever the situation is. Natural selection is death, just like genetic drift. By the way, when we say random and because of some event, we're talking about death. All right, you know what I mean. Let's move on. Random because of some event, and we're talking about random death. Natural selection is also death, but it's not random. It has a reason. And we'll see. We'll look at the example on the next page. Are we all good with this?
Yes.
Yeah. We're going to move on. We're videotaping this. If you miss anything, find it when you get home and watch it. Make sure you put in your notes. I need to watch it here. So when you're going to watch the video, you don't have to watch the whole thing all over again. Just go to that spot. 100 white, 50. So let's take a look at this real carefully. This is I made this one up, so I was glad I didn't make a mistake. So you have 100 white and 50 black doves, right? We're feeding in the park, and a crane, like one of those construction cranes we have up in front, falls and kills 48 black doves and 2 white doves. All right, 2 white doves, and it just happened the black doves die more often than white. In this example, which of the following would you think?
Drift.
Genetic drift. Do you see why it's not natural selection?
Yes.
Because it's random. It's random. I know a lot of people chose. I saw that a lot of people chose natural selection. Yeah, but natural selection is not random. Natural selection, you get chosen for a reason. It may be, the reason is not predestined, right? In the theory of evolution, in the explanation that we use, evolution is something that, it's a law. We see it. We see evolution. We measure it. But the theory of evolution, that's the explanation behind evolution, we don't use, in science, we don't use a benevolent being, a God, that guides it. Now, you might believe in a God that guides it, and that's fine. But just so you know, when I say there's a reason, what I mean is one thing out-competes another thing, right? So a heart without a hole in it allows the person to live longer, do more work, get more food. Therefore, that person can have more babies. Does that make sense? But it could be anything. It could be any one of the 10,000 different traits that you have, 100,000 different traits. Any one of them can give you an advantage. An advantage over what? The poor person next to you that doesn't get to have as many babies as you. So in the context of evolution, think about it this way. You don't have to be faster than the bear.
You gotta be smart.
You got to be faster than the person next to you.
That makes sense.
Does that make sense?
Yeah.
So natural selection it's a competition, but there's a reason why. I know it's messed up, but it's true. It's messed up, but it's true. And so that's life. That's what we're dealing with. That's nature, right? When you watch Nature Channel and you see the little baby, sick, poor little gazelle hopping over to the watering hole, right? And you see the big, strong gazelle coming over, and it can jump really fast, come over the watering hole. And then you see the crocodile start moving towards him. And the crocodile, the one that's tall and fast, jumps out of the way. The poor little hurt, beautiful little sweet, big, doe-eyed gazelle gets eaten. Oh no! Bambi's gone. That's sad. I'm sad too. I don't really even like to watch those shows because it bothers me. But the point is, that's what happens, right? The one that isn't hurt, the one that does whatever it did, whatever genes it took to be the one that wasn't hurt, that's the one that survives. So natural selection really does move things. But there's, as far as we can tell, remember what makes it something better fit to survive, what we're talking about, that changes with the environment. If the environment changes, the things that were best fit to survive last year aren't going to be best fit to survive today. So you're constantly competing. So in that sense, evolution has no direction. We're not moving, there's a lot of movies that talk about evolution. We're moving, going to evolve to this greater ascended being. That is not what we're talking about. We're talking about life competes and competes and competes. And as the environment changes, life changes. All right. A population of moths. There's black moths, there's white moths. 3 white moths and 15 black ones are spotted. And there's 15 black and white spotted moths, right? So 5 black ones, 3 white ones, 15 black spotted ones. All of a sudden you change the environment. You see there's a change in the environment. The change in the environment is you got soot. People are starting to make a lot of dirt. Soot is dirt, black dust. It turns everything. This happened in England, by the way. Okay, guys, focusing. Black dust covers everything. Think about it. If you are this predator, if you are this, let's say you're, an owl, okay? You're an owl. And everything's covered with dirt. I'm glad everybody put whatever. I wish you'd listen to me instead of talking to one another, though. And I'm just going to use white, and so you're hunting, and here, you're hunting, and you see this white. Guys, you're not, I can't deal with the talking. If you're talking, I know you're not listening. So these moths are flying around here. So there's 3 moths there. Do you see the 3 moths? You're hunting. You are an owl, or you are some kind of bird of prey that's eating moths. Moths are very delicious, and by the way, owls do eat them. Well, they're delicious because I see the animals wanting to eat them. They battle each other to eat them. I never ate a moth, but I'm assuming they're delicious. I've never eaten one. I don't like eating. Guys, you're missing the point. There's 3 moths up here. You're an owl. Which one are you going to choose? The white. The white's the easiest one to see. Why didn't you eat the black one? You can't see them. So over time, the white ones are gone, man. If you're going to choose between the spotted one and the black ones, you're probably going to see the spotted ones first. And if you're going to see do you see the black ones? I don't see them. So when we're talking about this, which one happens over time? Do the black moths increase in number? Yes, they do. A decrease of the black moths? No. That doesn't make sense. You just said it increased. Increase of the white moths? No, that doesn't make sense. They're dying. A decrease in the white moths? Yes, you do. So if both A and D are right, then it has to be E is the answer.
I should have read the whole question. That's the problem. I didn't read the whole question.
Hey, those of you that complain after the quiz, you got to get it right on the quiz, not after. So I mean, I'm not throwing shade or nothing. I'm just telling you because I heard someone say I'm throwing. Look, you're gonna get on this test, right? And nobody. And I know you're all gonna say, "Oh, I thought I shouldn't have changed my answer. I thought I knew it was this," and I said. And we're all gonna, and hey, I do it too, we all do it, and it's not gonna matter if you don't get those scores. I mean, that's all the state cares about, just very, very clear. It's a computer that runs it, they don't even have people reading it. So just be ready. It's a harsh, harsh world. Just like that bear example. Yeah. It's just harsh. It's not gonna matter. All right. In problem 6, and I mislabeled this one, it said 6, it should have been 7. Which is the most likely reason for this change? Is there a reason for this death?
Yes.
Is there a reason for the increase in black moths and decrease in white ones? Is there a reason, or was it at random chance?
There's a reason.
There's a reason, so it's D.
I got that right.
Now the reason doesn't, according to the theory, according to the explanation, the reason doesn't need guidance, right? It just is a reason. All right. This particular question, these two questions I already answered for you in an 8-minute video. We're done. Watch it. It's like I only made it 8 minutes. It's all it took me to answer. So let's go through these answers real quick.
Yes, sir. I really like your class.
I thank you. Is it time to go already?
No. We packing up. Our papers out.
Oh, okay. I don't know what's going on. It's 157. Every time I hit 57, I start twitching. It's
You start twitching. Now that's some other stuff. I do not know. Oh, I'm sorry.
All right. So let's look at this. When I read this, it says, given a problem in Hardy-Weinberg, the equilibrium with a allele frequency, given a population in Hardy-Weinberg equilibrium, what does that mean? That means what?
It's equal.
That means there's no evolution, right? The fact that you have Hardy-Weinberg means there's no evolution. Are we clear? All right. So it says, given a population, we're making the video now, guys, just so you know. Given the population of Hardy-Weinberg, that means that there's no evolution. The gene pool is stable. That's what that means. With an allele frequency of 0.9 and a little a of 0.1, determine the frequencies of the three genotypes, big A, big A, big A, little a, little a, little a. Well, if you know big A is 0.9, there it is, and you know little a is 0.1, then you know p squared is 0.9 squared, you know a squared is 0.1 squared, so the frequency of the genotype big A is 0.81, the frequency of the genotype little a is 0.01, and of course you still have to figure out the heterozygote. That's 2pq, so 2 times 0.9 times 0.1, which is 0.18, and that's your three genotypes, just that simple. So if you have your allele frequencies, you just plug and chug. You have to do some squaring, but sometimes you have to do some square rooting, as you see in the next problem. In fact, let me just get rid of these and just do it again.
So that little
Even though, see how beautiful it was? I'm so sad that I had to do all that
I
work.
have a question. So that Z right there,
I'm
that's
just-
the recessive, that's little z?
So I just want you to, I want to go over it with you together. I'd rather go over it with you. I'm hurt because I worked so hard on it, but. All right, so let's go ahead and do the next one. Let's do this next one together, just like we just did. You guys should be able to do this one on your own, but if you didn't, you can rewind the video and watch it again. So in a population of Hardy-Weinberg equilibrium, what does this mean again? No evolution, stable gene frequency. The frequency of the little z allele is 0.6. So little z is 0.6.
So big Z 0.4.
Nah, hold on. So that's the frequency. So she's right. We can look at the...
That's supposed to be 6.
Oh, yeah, thank you. So she's right. You said 0.4, and that's what my hand wrote. All right, so we got P plus Q equals 1. So if they tell you the little allele, which is which?
Little z.
Is it Q or P? It's Q. So 0.6 equals 1, or P plus 0.6 equals 1. What is P?
0.4.
0.4. So little z is 0.06, and that's not really true, is it? The frequency of little z, so I should put this, the frequency of little z is 0.6, which equals what? Q, right? Then P is equal to the frequency of
Big Z,
big Z, which is turns out to be 0.4, because look, think about it for a second. I know there's some of you out there that don't understand this, so think. If you have a gene pool that's all the genes in the population, and more than half, about 60%, are little z's, right? Then the dominant allele is what? If this is the 0.6 here, what must the dominant allele be? The rest of it, right? If these are the 0.6, and what's the total? 100%. So if 60% is little z, then 40% must be big Z. That has to equal 100, right? So let's remember that moving forward. That's where you get this equation. That's why this equation is true. So P equals 0.4. So they're asking what the percentage is in the population of the heterozygote. Now that's easy to calculate, but who can tell me how to calculate it? Not you, because I know you know. I want somebody to think. I want someone to try it. Be academically brave. Give it a shot. Yeah.
Okay, so you're gonna use that P, 2 PQ.
2PQ.
And then that's when you're gonna put 2 parentheses,
So 2 parentheses.
0.06,
So 0.06. You see where she's getting at?
Yeah.
Times what?
0.04.
0.04.
I don't get what she getting at.
0.06.
You mean 0.6?
It's point
Oh,
six.
she's right. She said 0.06 and I wrote it. She meant 0.6. She meant 0.6. It's a simple mistake, although we need to make sure we don't make it on a test, right? Do you see how simple mistakes can be made? All right, so 0.6 times 0.4 times 2 is what? What's... Someone do the math. There's calculators all over the room.
0.24.
So then your heterozygote here is indeed 24.24. But did they ask, if I wrote that answer on an essay in an exam, guess what I would get in college? It ain't most everywhere. I would get this. Was this not the answer? Oh, she didn't multiply times 2. All right, what is the number?
40.
It's what?
40.
0.48? Are we sure we got that right? Do I have to do the math myself? All right, so if I wrote this on the test, I would be wrong. I would get the answer wrong because it's not in percent. So thank you. You have to answer the question you're asked. Is that clear? They're asking you percentage. You got to give them percentage. What's the percentage?
48%.
48%, because when you're going from decimal to percentage, you move it twice to the right. All right. What allele big W for white is dominant, so I like to big W equals dominant, and that's white. Well, I'm just like to write down the information I know. And then I see little w is recessive, and that turns out to be black. I like to write that down. And then it tells me that 900 sheep. What is 900 sheep? What does that stand for?
The gene pool.
The gene pool, or the total population, right? It's not really the gene pool because they say 900 sheep. They don't tell you the genes, but that's the population. But you get the idea. You're right. That would be somewhere in there are the genes. And you got 891. Out of this 900, 891 are white. And 9 are black. Estimate the allelic frequencies, the frequencies of the alleles. All right, so let's take a look at that. How would we do that? So that's me writing down what we know. How do I tell frequency? What does frequency mean? Who can tell me?
Okay.
Yeah.
Frequency is the percent that's
So how do I okay, but yeah, it's in this case a percentage, but how do I find that? I know you know, dear. I want someone else to answer. I want someone else to just, come on, I want to encourage you to be brave. You sitting there and writing stuff down is fantastic. You asking questions and getting something wrong now is so much better than you getting it wrong on the quiz. What is the frequency here? How do I find the frequency? Yeah. No. Yes, ultimately you're going to use the frequencies in that, but you have to find the frequency. No. Yeah.
If you're gonna put like the part of, for example, 891 over 900, you're trying to find the decimal, and you get to like.
No, you're gonna look.
Well, the first part is the problem with using this. We can't really use the white. Who can tell me why we can't use the white one? Yeah.
We don't know if it's like that capital A.
That's right. We don't know if it's big W or big W little w. So we're looking for the allelic frequency. And that's the alleles. This is what? What are we looking at here? What are we looking at here? This is phenotype. There's a lot of talking going on, and I think some people are missing this. So it doesn't really help us. The white ones don't really help us very much in solving our problem. Which ones do we need? The black ones. Why do we need the black ones here? Because we know they're recessive. So we know this is little w. That is a big number. That's a big idea. We know that this is little w. So what does that equal? What is 9? What is that going to equal? What is that going to give me? The frequency of the little w gives me what? Q squared. That gets me Q squared. So you got to get that. If you get the frequency, if you get the phenotype, you need to know what is the frequency of the recessive phenotype. Because then you got Q squared. And the magic, then you just open the box. Everything else flows out after that. So now you got Q squared. But what is Q squared? That's the frequency of black. So what's the frequency of black? How do I calculate? It's not 9. 9 divided by what?
900.
9 divided by 900.
Which is 1%.
Which is what? 1%. Or that's right, 0.01. And that's the number we want to use. So when we how do we find, if we know Q squared equals 0.01, how do we find Q? Yeah.
We're going to, since, P plus Q equals 1, right?
Well, we're not there yet. We have to find Q. Right now, all we got is Q squared. How are we going to find Q?
Divided by 2?
No. You got to take the square root. You got to take the square root. And when you take the square root of a number, of a number that's squared, you go back down to the base, right? If you remember that. So Q squared, the square root of Q squared is Q. And that equals what? What's the square root of 0.01? Who's done the math? Somebody have a calculator? Square root of 0.01. What is it? You got it?
No, ma'am, right there.
Oh, yeah, go. What is it? No, it's not 0.000. Let me see the calculator. I'm depending on you guys to use the calculator work, but.
I don't know how to use it.
All right, so somebody said 0.1, but I don't trust you anymore. You guys hesitated too much. It's 0.1. All right. Well, I hope you can do it on the test. You're so adamant about this. So, 0.1. 0.1 is Q. We still don't have, we got Q, that's great, but we still don't have P. So we only have half the allelic frequency. This is one half of the answer right here. How do we find the other half, which is P? Yeah. That's right. Or let's start from the beginning. You're jumping again. It's P plus Q equals 1, where Q, you could think of it as 1, or you could think of it as 100%. And if you think of it as 100%, then 0.1 becomes 10%, right? And so when you look at Q as 0.1 equaling 1, then P is what?
9.9.
Then P equals 0.9, which is 90%, right? So then we can say P equals 0.9, and that's our answer. So that's our allelic frequencies. We can say that but do they ask us for percentages in the problem?
No.
They don't ask for percentages. We could give them a percent because they don't ask for either one. So we could say 0.9 or percentages. But we're going to go ahead and just say, look, it's 0.1, so Q is equal to about to 10%, and P is equal to 90%. Or you could leave it as decimals, whatever you want to do here, okay? So that's your answer. That's how you do it. All right, so let's go ahead now. Let's take a look at this one that's already done for us, as I did it last night. Yeah?
So they will never know, like, if it's heterozygous.
Oh, we could do the heterozygous if you want. That's a really good question, right? What you're talking about is not the allelic frequency, right? These are the allelic frequencies right here. There's only two alleles. These are the frequencies of those alleles. But now if I ask you for the genotypic frequencies, now we can do, well, what would we use to do that? Well, what we would do is we used our formula P squared plus Q squared. Oh, that's not right. Everybody's ready to jump on me too. 2PQ plus Q squared equals 1. And so we could say, look, if we want our genotypic frequencies, we got, in our genotypic frequencies, if we want how many big A's you have, how many homozygous dominant, then you'd use P squared, which is equal to what? 0.9. We use the decimal form, not the percentage. 0.9 squared, right? And you can do the math on that. I'm not going to do it. And then if you if you want to know little a, well, that's easy. That's Q squared, which equals 0.1 squared. And if you want to know the heterozygotes, then, in other words, you want to know big A, little a, then you go 2PQ, which is equal to 2 times 0.9 times 0.1, right?
Oh yeah.
So, but those are genotypic frequencies. Those are genotypic frequencies. We don't have to do that because that wasn't asked of us in the problem. Guys, I'm hearing a lot of talking. I really would rather you guys just focus and let's get through this. Let's just get rid of all this work. Look at all that work we did. I say we, I mean me. All right, so did you guys do a decent job of getting these answers on your own?
Yeah. I got all of them.
All right. Well, you guys, you can see how quickly we could do it. We can do it quickly. If I didn't have to explain this, I could do this in 20 minutes, right? All these, and hopefully not make any mistakes. All right. Yellow corn, 1,000 kernels. White corn, dominant. Yellow corn is dominant. Recessive allele is white. 1,000 kernels, 910 are yellow, 90 are white. You two stop it. Last time I'm going to warn you. 1,000 kernels equals what? What is this? What does 1,000 mean? It's the population. And 910 are yellow. When yellow are dominant. So let's say what? What do you want to call it? Want to give it big Y? Blank, because we don't know what it is. Very good. Somebody said that's excellent. That really makes me feel good. So 90 are white. Now this is an important one. It's the white one that I like, and that's the one everybody should like, because the white one is recessive, and we know those numbers, right? In this case, it's the white one, depending on whichever is recessive. So, anyways, what are the frequencies of yellow and white alleles in the population? Well, if yellow is 910, what's the frequency of the yellow? We need to find out this one. This is the one we need to find out. So what's the frequency of, what does this equal, by the way? What does little y equal? Q squared. Somebody was listening. Q squared, the frequency of white is what? 90 over 1,000. Very good. And what is that percentage?
0.009.
Point, what?
009.
0, 0,
0.09.
0.09 or 0.009? What it, not 0?
0.09.
All right, you said like 3 different answers, so chill.
I said it right.
All right, so anyways, 0.09 or 9%, right? But we're going to leave it at decimals. We need to figure out what is the question. They want to know what's the frequency of both alleles, so we have to find out what p squared is. So if q squared is 0.09, how do we find out what p squared is? You want to do 910 over 1,000. That's not how we do it.
P plus Q.
Because this is both the big Y, and big Y, little y.
P plus Q square root of.
Well, what we got to do is we want to use P plus Q equals 1. We can't use that because all we got is Q squared. So we're going to take the square root of both sides, and we're going to take the square, which we're going to do if we want to find Q squared is equal to 0.09. I hear a lot of conversations. I wish you would listen. You better listen to it tonight as you get this, because I'm going to finish this in the next class. When we do that, that's Q equals what? What's the square of 0.09? Someone do the math on a calculator. What's the square root of 0.09?
0.9.
Give me a calculator. It's 0.3 is correct. So 0.3 is your answer. All right, so I'm glad to hear that some people were guessing well. You were using your minds. Wherever you were making mistakes, please don't get up. Listen to me. I know class is over. Just wait a second. Please watch the rest of this. We're not even done with problem 4 here. And then I'm going to go over the case study. The case study will be due on Wednesday. So make sure you watch this video as soon as you can. So you got 2 videos to watch. The rest of this one and the little short 11-minute one. You got that case, the work you need to do. You need to get it done. Don't forget. So, what?
0.49.
So that's 0.49 is the frequency of the P genotype, the homozygous dominant, right? And that's equal to 49% if we have to put it in percentages.
Yeah.
Did the problem ask us to put things in percentages?
No.
No, so we could have left it at 0.49. We could have said 49%. And they're not, what are they actually asking us? They're asking us the frequencies of yellow and white alleles. We already figured that out, didn't we?
Yeah.
Where did we figure it out? Let's go ahead, let's surround it in orange. Where did we figure it out? We figured it out here, right? This was the frequency of, oh no, that's not it. Where did we figure out the frequency of the Q allele?
In the red, right under the.
This, right? Q allele was here. That's our point. That's the frequency of the recessive allele. We took Q squared and we figured out, well, we take the square root of both sides, that gives us what Q is. Where did we figure out the frequency of the P allele?
Right there.
Or rather the dominant allele.
Oh, the allele?
The allele itself.
Oh, P plus.
Where did we figure out P? We figured it out here, right?
Yeah.
That's where we figured it out, didn't we?
Yep.
Because we didn't write it out, but we just discussed it in the diagram. But if we want to write it out, we would say P plus 0.3. Where do we get 0.3?
The frequency.
The frequency, which equals P must equal 1 minus 0.3, which is what? 0.7. And 0.7 is 70%. What we did is we kind of drew it out, didn't we?
Yep.
But I don't care if you draw it out or you do the calculation, you still got 0.7. That's how you figure it out. Over and over again, what you're going to see is you find the recessive genotype, and that gets you P squared, and then you find the recessive allele frequency by taking the square root, and then you use P plus Q equals 1 to get the dominant allele frequency, and then finally you can use that, square that, and you get the allele, the dominant homozygous frequency. You give me that face like you just drank some sour milk. Did you understand that? No. Okay.
I just know you squared something and you took the
Yeah, I know, and you gotta do some work on this, okay? So try to do these problems, try to go back over it. I literally walk you through it step by step, and we're kind of stepping in the middle of these programs, so you're supposed to have already tried to do it last night and kind of walk through it. In that short little video that we did that I sent you, it's 8 minutes long, I did walk you through it. Go back and do it again, and we're gonna do a couple more examples, and hopefully by the time we're done with the examples, you're getting it. Okay, watch that video again, I'll send that video out from that Bozeman Science put out, okay? All right, so let's take a look at the next example. So that takes care of 4. You know, this stuff, it can be very easy. It really can. But it also can be it can get real complicated real fast. And one of the things you're going to have to do is you're going to have to memorize the vocabulary. You're going to have to memorize what it means to be heterozygous, what it means to be homozygous dominant. You're going to have to memorize that in order to make some of this stuff make sense. Okay? I mean, that's all I can tell you. All right. So let's walk through it again. The compound, there's a compound PTC. It tastes very bitter. I mean, it tastes horrible from what I'm told. I'm a non-taster. I can't taste it. I had some PTC paper, this little piece of paper you can put on your tongue. If you taste it, it's like eating, I've been told that it's something really horrible, I don't know. It's something, I can tell you that people have this, like, you see their faces turn really horrible. They drink a lot of water. They try to, I don't know. They say it's really bad. I can't taste it, so I can put that paper on all day. So, anyways, it's the inability to taste. The fact that I can't taste it is a recessive allele. So I actually have the recessive allele to this. So I would be now. Pay attention. I see there's some people that don't understand this yet, are not looking and not paying attention. So I'm like, okay, well that explains why you don't get it. So the recessive allele would be little t, little t. So that's what I have, little t, little t. So as soon as I see recessive in my mind, I automatically jump to this, which is what? Homozygous recessive. And which is in what? What variable? P or Q? Q squared. So that's what I'm thinking already. You see how my mind works? I see recessive allele, I'm automatically jumping to this. That gets me to this, that gets me to Q squared. If your mind isn't doing that, you haven't worked on the vocabulary enough. Okay? In the American white population, about 70% can taste PTC. And about 30% cannot. All right, so what does that tell me? When I see that, am I thinking genotype or am I thinking phenotype? Phenotype. I hope you said phenotype. So when I say tasters are dominant, right? So I have to know that. And recessive are not tasters. And I say the phenotype, I have to remember these are phenotypes. If I start to try to put, let me tell you right now, I start to put 0.7 or 0.3 into any of these equations, it won't work. Actually, 0.3 will, but not 0.7. So dominant tasters are 0.7. Why? How come I put 0.7, not 70%?
Because it's still the same.
This is the same, exactly. But why do I put 0.7 instead of 70%? Because that's what I got to use. I can't use 70% in my calculations. I have to use 0.7. So what's non-tasters? What am I going to put?
0.3.
0.3. Okay. So which one of these is going to help me? Marion, which of these is going to help me? Which one's going to help me in my calculations? Is non-taster, the fact that I got 70% non-tasters, is that going to help me get numbers? Why not? Why can't this help me? Why is that no good, that number? Why doesn't it help me? Well, think about it. Non-tasters, I mean, they're tasters, they're dominant. Does that tell me anything about the allele frequency? Why not? I know they got a big D, I know they got a big T. Well, here's the thing, Omarion, is that this could have big T, or it could have big T, little t. And so I can't tell if it's dominant or reset or heterozygous. I can't tell if it's homozygous, dominant, or heterozygous, because you can't tell that by looking at something. What can I tell, Omarion? What's the one thing that can't? What? Yeah, I know the phenotype, but there's two different genotypes that get me the same phenotype. That's the problem with this number. This includes two different groups. What about the other number? What do I know about the other number? I can't hear you. I say again.
I'm not sure.
Okay. So when I see 30%, because it's recessive, I know it's little t. What do I know about little t, Omarion? It's recessive. What else do I know? Yeah, what else do I know? That's q squared. So I got q squared. That got me where I need to go. All right. So q squared equals 0.3. I got to find out what? Estimate the frequency of big T. I got to estimate the frequency of little t, right? And what else do I need? In this population, as well as the frequencies of the diploid genotypes. So diploid genotypes means the genotypes. Diploid means two genes. So haploid would mean if they're gametes, right? Diploids are your somatic cells. So that means big T, little t, and big T, so all three. So diploid genotypes would mean big T, frequency, big T, frequency, and little t, frequency. What are those frequencies? That's what they want to know. So we have 0.3 equals q squared. How do I go from that to finding out the frequency first, the allelic frequencies, or the frequencies of the alleles? Good, Omarion, good job. So you got to go the square root. So we take and we find the square root of q squared, the square root of 0.3, and that gets us q, doesn't it? What's the square root of 0.3?
About 0.55.
0.5, square root of 0.3, you're saying is 0.55?
About 0.55.
Let's just go with 0.55, I'm good with that. All right, so we're good. That's the frequency of, so what does that tell me? That tells me that about 55% of the alleles in that gene pool are recessive alleles. That's what that tells me. Now the next question is, what about the P? What are the question? Where can that lead me? That can lead me to try to figure out the P. How do I do that, Omarion? What am I going to do? If I know 55%, now let's think about it. I'm going to draw it out again. Pay attention to what I'm drawing and think about it. This is the whole population. This is all the people on the planet. In this case, all the white people, right? Because that's what they say. I don't like that. I don't like American white population. You know I don't like that, but that's part of the problem. So that's the population we're talking about. Q equals 55%. So about a little more than half is what? Little t's, right? That's little t's. That's not genotypes, right? That's alleles. There's 55% of the alleles in the whole population are little t. So what's the rest? Big T, right?
P plus Q.
And so what is that? 45%. And what's another way of writing 45%? 0.45. You see that? You see, that's all there is to it. Now another way of writing it would be P plus Q equals 1. The 1 represents this whole thing. The whole gene pool is 1. Another way of writing it could be 100%. You can write it that way too, but 1 can be 100%, just divide everything by 100. All right, so if P was 55, if Q was 55 or 0.55, then P must be 0.45. And those two together must equal 1. Is that true?
Yeah.
So we're good. That's the beginning. That tells you. Now think about it. Think about why that makes sense. you got to remember your equations, and you got to remember your definitions. If you know your equations, your definitions, it's all you need. You got P, you got Q, you got everything. So let's do the math. So P equals, we know already, we just said it, right? 0.45. By the way, which of these is there more of, the recessive alleles or the dominant alleles? See another example that not always are the dominant alleles more often in the population. It's a common misunderstanding because of our usual use of the word dominant, right? Dominant means there's more, right? But that's not the case. Dominant in this case just means it shows up if you have it. All right, P equals 4.45, Q equals 0.55. All right, that's fine. Now that tells us this is what we call allele frequency. Now the question is, what about these? How are we going to figure out these? Now, Omarion, this comes to our definitions again. What does big T equal in our definitions? Let me give you the equation. You ready? P squared plus 2PQ plus Q squared equals 1. What is big T equal to? P, good. P what? P squared. You said it with a question, but you need to know it. So put it on an index card, tattoo it on your eyelids, so you go to sleep, that's all you see. Look up, put them on the ceiling, paint them, get a ladder and paint them on the ceiling. Whatever you need to do, just make sure big T, the homozygous dominant is P squared.
Yeah. So
what is big T little t in this equation, Omaria? What is it? No. What's Q? Somebody else help me out. What's Q? Q squared is what?
Recessive.
Homozygous recessive.
Yeah.
So that would be little t, little t.
Yeah.
What's big T, little t in the equation, Omaria? That's right. 2PQ. See, that's what you could have learned from the video that I sent, that 8-minute video that helped you. Right? Okay. So the heterozygous is 2PQ. So the Q squared, we already knew that. Didn't we know already what Q squared was? They told us what Q squared was. Q squared is going to equate to the number of recessive individuals in the population, the people that can't taste it, and that's equal to 0.3. Do you remember we figured that out already?
Yeah.
P squared is what?
0.45 squared.
There it is. Somebody said it perfectly.
Yeah.
0.45 squared. Somebody do the math.
20%.
What is it?
20%.
Yeah,
So 0.2?
Yeah, about.
Then the rest is going to be 0.8.
And so what's 2PQ? That would be what? Let's do the math. Let's not skip steps. 2 times what?
Times 0.20.
No.
0.45.
Good try. But look, what is 0.20? What does that equal to? P squared. All right, do you see any square here? No. This is 2PQ. So what's P? 0.45. And what is Q?
0.55.
0.55. You got to be careful with this. And so somebody do the math. What is it?
About 50%.
0.45 times 0.55 times 2 is
0.495.
let's say, all right, let's just say 50. So these should, again, it's an estimate. There've been some rounding errors, but this should all equal how much?
1.
It should equal 1 or 100%, right? 30. So we should be able to add these up and equal 1, right? Isn't that what this says? Okay, so let's see. 20 plus 50 plus 30, it's 100%. 100. Or 0.2 plus 0.5 plus 0.3 equals 1. So I can check myself. I can check my work. Because I labeled it, I did it carefully, and I wrote it neatly. I can go back and check my work and make sure that everything's right. And I just did, and you can see it all equals 1,
Yep.
which is 100%. Does that make sense?
Yeah.
All right, let's go try another one.